Hi, my name is Aaron Goldsmith. I'm a tutor for actuaryexamtutor.com. We'll be finishing the review on what you need to remember from calculus as you're studying for the P exam. This final section is on exponentials. And so when you hear compound interest, at least with these first two exams, you're going to think of the FM exam. However, I'm going to use it just to introduce the exponential function and the number e. It was Jacob Bernoulli who first started studying continuous compound interest around 1680. And the first time that e was effectively used as a number. This is the relevant function. If you have some number x and a large number n, then 1 plus x over n will be something that's slightly larger than 1. And then if you multiply that by itself n times, depending on how close it is to 1, it might converge to 1, or it can converge possibly to a number, or it could diverge to infinity. And we'll see in number 2 here that it does converge to a number. And so that's for fun, because it's not going to help you all that much on the P exam. So just don't bust your brains on it if it's a lot of work. It's just it's amusing. 3 is also amusing. It shows you why the derivative of the exponential function e to the power x is itself e to the power x. So it's a quick one-liner, but it's not going to be something that you refer back to as you're taking the exam. So these are just for fun. If you want help on them, then I would be glad to give you some hints. Number 4 is a useful integration by parts I mentioned in the last video. If you're integrating any polynomial times the function e to the minus x, then it comes out to this. You sum up all the derivatives of this polynomial and tack on a minus sign multiplied by e to the minus x. So you know how to just chug that out. You don't have to use integration by parts several times over. So this will be very useful if it happens to come up. It's not too bad to remember. You can check it if you want. Just take a derivative and make sure that it all cancels out, and you take derivatives of both sides, and you should get q of x e to the minus x on both sides. Taylor approximation and Taylor series, I think, are often made to be more difficult than they are, so I'm going to try to elucidate them now. The idea is that you have a function, you don't have the explicit form of the function, so you can't just plug in a number and chug out the result. You do know how to take derivatives at a single point and evaluate those. So you want to try to get the behavior of the function at that point and use that behavior to guess how the function is near that point. So this is the Taylor series right here. The first Taylor approximation is this number f of 0. It's saying if I were to try to approximate the function f near x equals 0, and I could only give one number, my best guess would be f of 0. And it's a continuous function, so you know that it's going to be close just by the definition of continuity. Then this next term is the linear approximation, and it's something you should have been doing already in a calculus class. It's just finding the tangent line at a point. It still goes through the point 0 f of 0, but it has the slope now. The slope of the tangent line is f prime of 0, and so the slope matches the function to this approximation, and that'll give you the right direction of changing. If the function's increasing or decreasing, then at least your approximation will match that. These later terms are just to make sure that the approximation continues to get better near the center and kind of hug the graph of the function tighter and tighter. I do want to give a warning that in real life, the approximation generally does not give good information about the function distant, like far away from the center. In classrooms, you approximate sine of x, and it converges everywhere, and it's amazing. But this is a rarity. In real life, then you have an interval that you should stay in, and have a good approximation only close to the center value. So these are two good series to know. E to the x has the series 1 plus x squared over 2 factorial and so on. You can take derivatives of this to see that the derivative of e to the x is still e to the x. And that's by the derivatives at 0 are all 1. So if you plug in 1 for all these derivatives, you get this series. And then 1 over 1 minus x is the series where all the coefficients are 1. You could check that by multiplying both sides here by 1 minus x. Let's do some examples in a Desmos. Here we have a couple of functions that we're going to find the Taylor approximations for. This first one is x cubed minus 2x squared plus x minus 1. And these are all going to be centered around x equals 0. So the first thing you do is plug in x equals 0. All this stuff vanishes, and we're left with minus 1 as the first Taylor approximation. Then you get this horizontal line going through the graph at the point x equals 0. The next thing we do is take one derivative and then plug in x equals 0. So you'll get 3x squared minus 4x plus 1. And then these will drop off. This vanishes from the derivative. And then we get this 1 here for the slope. Our next Taylor approximation is going to then be, we're going to keep this minus 1. And then 1 will be the slope of the line. So there we have, and this is the tangent line to the graph at x equals 0. That's our next Taylor approximation. All right, so that's even better. If you stray a little bit from 0, you're going to be going in the right direction at least. And then finally, for the second derivative, we get the second derivative is 6x minus 4. And plugging in x equals 0, you get minus 4 there. So plugging in the formula, minus 4 over 2 gets this minus 2 coefficient. And so our third Taylor approximation is this quadratic minus 2x squared plus x minus 1. And then again, you'll see that it fits the curve a little better around x equals 0. In this case, since it's a polynomial, our Taylor approximation is just pulling out coefficients from the constant on up to higher powers. You'll notice that this exactly matches. If we were to take another approximation, we would just recover the whole function, and it would align exactly. This Taylor approximation is not interesting for polynomials. So we have another function, cosine x, and we want to find the Taylor approximation of cosine x centered around x equals 0. You plug in x equals 0, cosine of 0 is 1. So we get a horizontal line passing through the curve at the point x equals 0. The next, we take a derivative, you get minus sine x, plug in 0, and you get 0 for the next, for the slope. And so this y equals 1 is actually going to be the same for the second approximation, because it's just, you see it's already tangent to the curve. Then the third approximation, we take another derivative. The second derivative of cosine is minus cosine. Plug in 0, you get 1, and there's always this dividing by 2 on the x squared part to account for taking the derivative when the power rule brings this exponent 2 down, and so that'll cancel out. You get, so the second approximation is y equals 1 minus x squared over 2. And so that looks like it fits around 0. You can't really tell the difference with how thick these curves are. All right, the fourth approximation is going to be, again, has a 0 because the derivative goes back to sine, and you plug in 0 to sine, you get a 0 there. There's no x cubed coefficient. The fourth derivative goes back all the way to cosine, so we get a positive number here. You plug in and you get 1 over 4 factorial is the coefficient. I'm going a little fast here just because this is review. And then our the approximation is 1 minus x squared over 2, and we get this addition x to the 4th over 24. And it hugs a little, it meets more exactly a little further away from 0.